Hello all. Welcome to today's session on free energy changes and biological transformation in living system. This is one of the 5 topics present in the Unit 1 covered under the syllabus Bioenergetics. Myself Dr. Mausmi Shankaradala, working as an assistant professor in the Department of Biochemistry, SJCWA, hereby gives a brief note on what is free energy change and how it is related in the biological transformation aspect in living system.
Learning outcomes will be including free energy changes and different definitions from the basics of bioenergetics.
Literature frequently claims that a living system seeks to reduce its entropy, defying the second law of thermodynamics to sustain its non-equilibrium, henceforth represented as NEQ existence, despite the fact that there is no universally accepted definition of life. Nonetheless, in accordance with the second law of thermodynamics, the determination of the direction of irreversible heat flux at the system reservoir interface is necessary to determine whether to reduce or increase the entropy of an open system. Because there are open systems in the surroundings, organisms obey the second rule by adding to the universe's overall entropy growth. Perhaps Erwin Schrödinger's annotation, which describes living things as metamorphically feeding on negative entropy, is the only source of the mistake mentioned above. Schrödinger goes on to a detailed explanation in the same monograph that talks about metabolism and in terms of free energy, represented henceforth as Fe, is a more relevant subject. He provided this explanation since thermodynamic free energy in any open system always falls during irreversible operations, in contrast to the Clausius entropy to which he was alluding. Schrödinger's discovery that physical laws and principles can describe biological systems had served as a foundation for numerous research projects. Organisms maintain biologically essential properties such as body temperature, blood pressure and glucose levels, which are distinct from ambient states. Living systems continuously exchange heat and material fluxes with the environment by performing metabolic work, which is subject to the energy balance described by the first law of thermodynamics. The second law posits that the entropy of an isolated macroscopic system increases monotonically with any spontaneous changes. Organisms and the environment together constitute the biosphere, which is isolated and macroscopic. Thus, metabolic processes in organisms increase the total entropy. The second law affects organisms by limiting metabolic efficiency. Comparatively, the total change in the free energy is unable to account for an organism's capacity for allostasis, which predictably governs homeostasis or more broadly its autopoietic characteristics. The level of individual organisms, but also at the ecosystem and planetary levels, and emphasizes the energetics and power efficiency in brain performance. By contrast, the ability of the organisms to undergo allostasis, which predictively regulates homeostasis, or more generally their autopoietic properties, are unable to be explained by the total change in the free energy. Allostatic ability is the main driver of the adaptive fitness, the emergence of which cannot be solely attributed by a biophysical self-organization from a myriad of emergent possibilities in the primitive circuits of neuronal activities. Organisms are under environmental constraints and adaptive fitness or natural selection, which is a consequence of successful optimization in specific environments during evolution. All living things rely on solar energy to directly or indirectly meet their energy needs. When there is a mass to energy conversion, it results in significant increase in disorderness. In the present diagram, you can very clearly see that there is a thermonuclear fusion from the sun which generates the photons of the visible light. Explaining the very known energy and mass relationship, E is equal to mc square. M is the mass and c is the velocity of the light. The nuclear reactions involve mass conversions into energy. For example, 4 protons are present in helium. Formation of helium from 4 hydrogens atoms is one of the most common nuclear reaction in the solar plasma. The net loss of the mass, which is indicated as 0.029 daltons, which is inversely used for the conversion into huge amount of energy. Henceforth, 1 dalton is equal to 6 into 10 power minus 24 grams or 1.66 into 10 power minus 27 kilograms. Here, 1 mole of helium is 4 grams and it contains 6 odd into 10 power 23 atoms. Therefore, 1 mole of helium, which is 4 grams in formation, will produce 2.7 into 10 power 12 joules of energy. Physics always deals with the several types of energy, including potential and kinetic in mechanics, energy in the form of light, sound, heat, electrical and magnetic, chemical transformation of mass and energy transformation between subatomic particles. Different types of energy include electromagnetic, light kinetic, heat potential, sound and waves are included under the subject of physics. Coming to the subject of chemistry, which always deals with the interactions between atoms through their outer orbit electrons in different solvent conditions, pH values, pressure levels and temperatures. Whereas biochemistry always deals with the way the atoms and macromolecules interact, which is similar to that of the chemistry, with the exception of typical pressure, temperature and pH levels, as well as the requirement for aqueous media. Explaining about the first law of thermodynamics, which is very well known, for any chemical or physical change, the total energy of the universe remains constant. In other words, energy may change transported from one place to other, but it cannot be created nor destroyed. The second law of thermodynamics, any spontaneous chemical or physical change is always accompanied by increase in the disorder of the universe. In other words, or the entropy of the universe increases in all natural processes. The interactions between electrons in the outer orbits of hydrogen, carbon, nitrogen, oxygen, phosphorus and sulfur produce the majority of the chemistry in the living system. The propensity of an atom to attract an electron is known as electronegativity. The most electronegative element is fluorine. Yet, the most electronegative atom in a biological system is oxygen. Enzymes catalyze a large number of events in biological systems that include the lone pair of electrons on nitrogen, oxygen, sulfur and phosphorus. A specific set of atoms that is constituting of a compound participate actively in a large number of complicated processes. They go by the name of functional groups. Because they operate at a constant pressure and temperature, cells are isothermal systems. Unlike other systems that can use heat emitted within the systems to accomplish work, they can only employ free energy. Plants create nutrients and obtain free energy from absorbed solar light. Utilizing these nutrients, both plants and heterotrophic cells convert the free energy in the nutrients into ATP or other compounds rich in energy. We refer to this process as catabolism. The process by which the cell synthesizes different molecules and ingredients using the free energy stored in energy-rich compounds is known as anabolism. In the current diagram, very clearly we can explain what is a catabolism and anabolism. On the left hand side, we can see the energy containing nutrients, which are carbohydrates, fats and proteins, which will undergo a catabolized reaction, nothing but breakdown, to produce carbon dioxide, water and ammonia. Whereas the precursor molecules like amino acids, sugars, fatty acids and nitrogen bases undergo synthesis, nothing but anabolism, which results in the formation of proteins, polysaccharides, lipids and nucleic acids. During the catabolism and anabolism, there is an occurrence of chemical energy in the form of ATP, NADH, NADPH2 and FADH.